welcome back. Today we are covering independent t-tests, so get ready for our tea party today. Last week we talked about t-tests for one samples. An independent sample t-test uses two samples, so you should be familiar with the procedure by now. It's just a little different when you have more than one group. We also talked about dependent t-tests last week, looking at differences between a certain group before and after some sort of intervention. Now we're looking at two complete different groups that we're comparing that don't take the same test more than once. So they're independent groups, or the score of one group does not depend on the other. So first I'll review just kind of a little overview of the different types of t-tests. And then we'll get into the details of independent t-tests. We'll talk about what the hypothesis is, how you test a hypothesis using an independent t-test. We'll talk about the distribution of the mean differences, because now that you're working with two groups, you are no longer just thinking about the distribution of all possible means, not just standard error like we normally do, but standard error of the mean differences between the groups. And then I'll run you through an example where we'll do some calculations. You'll get to do these calculations based on using standard error of the mean differences. And then we'll talk about effect size for the independent t. It's similar to the effect size that you're used to. We're just going to have to combine the information we have from the two groups. And then we'll talk about some controversies, issues, things that arise when you're running t-tests, multiple t-tests, that sort of thing. All right, so let's move on. The three different types of t-tests that we have are one sample t that we talked about last week, dependent or paired t, and independent two sample t-tests, the t-test that we'll be covering today. Last week we talked about one sample and dependent. Now one sample t-test is where you have one sample and you're comparing it to a population that you already have the information from. So for example, you wonder if this certain group of individuals with virus, if their body temperature runs higher than the general population. You already have the information from your general population. You know average body temperature is 98.6, so you're comparing how far are their scores from that sample compared to this population. You take that difference and then you have to divide by some sort of measurement of error. So you take that difference based on how far the means would be spread if you sampled over and over and over, the standard error. So you're taking the difference from that hypothesized mean of the population with this one sample, dividing by standard error to get your t-test for one sample t. But the key there is you're only looking at one sample, estimating is this group the same as this other population or not. And dependent sample t-test or paired t-test is where you have the same group, but you have two scores for that same group. So we use the example of you have them take a test, you get their scores, and then you do some intervention, you take their scores again. So there's a before and after. That's a paired t-test. And you remember the calculations for the paired t-test, you're still looking at differences. How big of a difference do you get in the sample of before and after scores? And is that difference that you get divided by standard error, but now the standard error is based on the distribution of those differences, if the null was true, if the average of those differences in the population was 0. So you're still looking at the difference between the scores, but here it's the difference, the average difference compared to the standard error of those differences. So with an independent sample t-test, it's similar. You're comparing two groups, but these two groups are different groups. Their scores do not depend on each other. And so instead of doing a before and after comparison, you do two complete different sets of individuals and you compare their scores. So let's move to an example. When we're hypothesis testing independent t-tests, you are going to compare two different populations or two different samples, but you actually draw information from both of those populations in the form of sample information. So sometimes you might have an experimental and a control group. You want to know if a certain drug works or if it's effective. So you test this drug for depression. Let's suppose you take this new drug and you test it out. One group, the experimental group, gets this drug. The other group, the control group, does not get the drug. They get something else, a placebo, a pill that doesn't have the drug in it. And then you compare their scores on some other variables. So maybe their scores on a depression assessment, maybe the VITAS depression inventory. And you look at, do the people who get the treatment, the drug for depression, the experimental group, are their scores lower or higher, if maybe the drug makes them more depressed, than the control group? So you're comparing two groups, but you actually have a sample. And hopefully, when this design is used, you randomly assign, if you're using an experimental design, you randomly assign individuals. So say you have 100 people with depression, and you don't just take, okay, volunteers to get the drug and volunteers to get the placebo, the pill without the drug. You randomly assign. So the reason we randomly assign to the two different groups is because you want to equal out differences. You don't want to get, maybe the most severe people won't volunteer because they're too depressed to think it would help them out. And so then you already have a difference between the groups to start with. You don't want that because you're not doing a before and after test. You're just comparing the two groups. So random assignment should eliminate or at least lower the chances that you get two groups that are different. Then you can just compare the averages of those two scores after they've already either gotten the treatment or the control. So the types of variable that you're using when we are using an independent t-test. Remember back when we talked about types of variables? Here you have a nominal variable and a continuous variable. The nominal variable is which group they end up in. Are they in the experimental group or the control group? Okay? So the two populations you're interested in, the group that gets the treatment and the group that doesn't get the treatment, those two different populations, that's your actual variable of interest, your nominal variable. And it has two levels. Here. The levels of that variable, they can either get the drug or they don't get the drug. Now, this is the type of variable that you would use for a t-test. If you had more than two levels of your nominal variable, say you tried out different doses of the drug. So you had a low dose of the drug, a moderate dose of the drug, and then a placebo control. You'd have three different groups. A t-test doesn't work anymore. So a t-test is useful when you have a nominal variable that has two levels that you're comparing. An independent t-test. If you a one sample t-test, you don't need those two levels. You just have one population that you're looking at. So you have your nominal variable. You also have a continuous variable. The continuous variable, you might know from other research methods, is your dependent variable. So it's the variable that you think depends on which group, which level of the nominal variable they belong to. You think that their depression scale, the score, will shift. That's what you're testing. Their score, that's your continuous variable. So their score on this depression assessment. So in an independent t-test, this is a valuable tool for you to use when you have two variables, one of them nominal with two levels and one of them continuous that you will measure to see if it depends on that nominal variable. Okay. I'm going to give you an example of something you might test with an independent t-test. My example is looking at supplemental instruction. Some of you may be familiar with SI or supplemental instruction. It's a program that they've implemented for historically difficult classes, and it's a supplemental program where you go a couple times a week and there's a peer tutor that kind of helps you out with your classes. So suppose I was interested in whether this SI, the supplemental program, actually helps improve your first exam score in a certain class. Your supplemental instruction, whether you attend it or not, would be our nominal variable. So remember, I can only have two levels. I can't look at people who attended a lot, more than once, more than twice. Here with the t-test, you can only have two levels. So let's just take everyone who ever went to this SI and people who didn't go to this SI, the supplemental instruction, and compare the continuous variable for those two groups, their exam scores. The t-test is going to answer the question about whether SI is really working in the population. Even though we know our sample differences, we might get a difference even without the population having a difference. So with hypothesis testing, the question we're asking are, do the samples differ enough? And you might put in parentheses, differ enough on this continuous variable. Do the samples differ enough on this continuous variable that we can conclude that the populations actually differ? You remember the example I gave you with my son's video games? He had small difference. He said, oh, the samples, my small samples don't differ enough that I conclude that difference is not just random sampling error, what I ended up with the sample. He said it's not big enough of a difference to conclude the populations are different. So we're still using the same hypothesis, hypothesizing about population differences. Here it's two different populations and two different samples to estimate those differences. So we say, are the sample differences enough based on the sampling distribution to conclude that the populations are truly different? Now, the distribution that this is based on is not just the one distribution, because now we're comparing two different samples to two different hypothetical populations, and we want to know if those populations are similar or different. So it's based on a difference of the possible means from each of those populations. So I have this illustration just so that you can get an idea of what we're talking about. First, on the top of this, you have population distributions. Okay, so and you can see these two are different. They're spread out a little bit. So there you have two different populations. So those would be, for example, the scores on the first exam. Okay, so for one group that attended SI, another group that didn't attend SI, and you have their scores on the exam. You can see there are some lower scores, some higher scores, but they both have an average that's different. Okay. And then right below it, the narrower normal distribution is the distribution of means. So remember this hypothetical distribution, this is like standard error for each of the groups. It's the distribution of all possible means if you sampled over and over and over at a specific n, a specific sample size. Now, the distribution that we're going to be using is not, so you have both of those. Which one do you compare your samples to? We're actually going to compare our test statistic to the difference between those two standard errors or distributions of possible sample means, and that's right in the center. If you took each possible sample mean and took the difference of those, you would end up with a normal curve. Most of the differences in the center, around the average of the differences, and then fewer and fewer as you taper off. And then the last distribution right down at the bottom of this table is just what you actually get from your sample. So here's your sample might look like this, even if it's taken from a normal population. And based on that sample, you're going to hypothesize what is the distribution of each population combined in the distribution of all possible means, the standard error, and then the pooled standard error, the combined standard error, the standard error of those differences of the means sampled over and over and over from each population. And it's important to keep in mind, you would never do this in statistics. You don't go out and sample over and over and over and over and over and over and create these distributions. But this is the theory. This is the basis of where our t-table comes from. So it's the basis of the distribution and the basis of how we calculate our t statistic when we're doing an independent t-test. Why we use the numbers we use is based on this theoretical distribution. All right. So before we go on, I'm just going to draw a picture. I'm going to draw a picture here of just a little bit. All right, so here's an example. If you have one population, the example I gave you just a second ago had two different populations. So the populations were different. It showed you how there would be a difference and the distribution of those differences of the means. But here, let's say that we have two populations that are identical. Because when we're testing statistics, when we're doing hypotheses testing, remember we're always testing the null hypothesis, the hypothesis that there is no difference between the two populations. So let's say we have population 1 has a distribution like this. Population 2 is identical. So it's right on top of it. I'm going to draw it just a little bit under it. So it's identical to this population. They're right on top of each other. They have the same mean. Okay? They have identical means. Now, will we ever know this, that the mean for these populations are identical? We don't know this when we're doing statistics because remember in inferential statistics, we're using a sample to estimate these populations. So we never know this, but we're testing this so that it's based on this distribution that they're identical. Pretend these lines are right on top of each other. Now, if this is true, if the null hypothesis is true, which means that the distribution looks like this. Both of the population 1 and population 2 are identical. So we could say that population 1 and 2 are these students attending SI and students not attending SI, the supplemental instruction. And this is their first exam score. And let's assume the null is true. So it doesn't matter whether they attend SI or not. It doesn't affect their scores. They both have the identical means on that first exam score. Now, if we were to take a sample from each of these populations, population 1 and 2, even though they're identical, we might end up with a sample mean, because remember the sample is not going to include everyone in here. We might end up with a sample mean right here for population 2 and a sample mean for population 1 that's right here, just because of who we ended up with in the sample, who we drew out of this population. Now we'd go, oh, there's a difference between these two means. Now we have to decide, is that big enough of a difference to conclude that these means are not identical in the population? And so if these are identical, most of the time, your difference in your samples is going to center around those two similar means, and it's going to be close together. Eventually, the difference of these is going to be centered around 0 if you're calculating the differences of these. Now, if the differences of your means starts to get bigger and bigger and bigger because you draw, different sample means that are always different out here, then it's not likely you're drawing them from the exact same population. So, taking that information and going back to some different concepts about the distribution of mean differences if the null is true. So if the null is true, population 1 and population 2 have equal means. Okay? Now remember, we never know this because that's what we're testing. We're testing with the sample information about the populations. But if the null is true, which is what we're testing, both means are identical. Okay? And if the null is true, the mean of the distribution of those means, so remember the distribution of all possible means from those two populations, so that's the standard error, the distribution of those means are centered around the same thing. Okay, so it doesn't matter whether your means were both 100 if you were testing IQ, that you take the standard error or the spread around those means, they're going to both center around 100. Okay? Now remember, as your sample size gets larger, that standard error, the spread of those means is narrower. As your sample size gets smaller, the spread is wider, but they're always going to center around the same number, whether it's 100 for an IQ or 25 for a different, maybe driving test. They're going to center around the same numbers. Now, if that's true, for a true null hypothesis where they're identical, then the mean of the differences between each of those groups is going to equal 0. So if you take all of the possible sample means and all of the possible differences between those means, most of those differences are going to center around 0, tapering off as you get further away. So this gives you an idea of what the distribution is that we're going to compare our test stat is going to look like. It's going to center around 0, the t-distribution, just like we talked about before. So let's go ahead and try an example. We're going to try this example asking the question, and this is from the Aaron and Aaron statistics book. If you have it, it's question number 4 under this chapter. So there's an educational psychologist who asks, she wonders if it helps students read if they're reading stories with their own name in that story. Okay, so for example, instead of using Dick and Jane's stories, common, just the typical names they put into these children's stories, they replace it with the child's own name. So if a little girl named Rachel is reading a book, it would say, Rachel climbed the hill. And it would use her own name instead of Jane. And this educational psychologist thought, well, maybe this will help kids to read, or maybe not. Maybe it'll distract them. But they wanted to see, does putting the student's own name in a story affect their reading ability? So they're not asking the question, does it make it better or worse? They're just asking, does it affect their reading ability? So we have this data table. You might want to copy down these numbers if you don't have it. It has 2 different groups, a group that read just the regular ordinary story with Dick and Jane in it, and the group that read their own name in the story. And if you notice that there weren't equal numbers of students, maybe the teacher didn't have an equal number of students to assign to these 2 groups, you typically want to try to get your 2 groups about equal, but calculations understand that you might not have exactly equal sample sizes, and so that's part of what we do when we calculate t is we adjust for the different sample sizes. So you have these 2 groups, one that read the stories with their name in it, and the amount of time it took them to read the story, and the other group that read the original stories. So these are 2 different groups. They're independent of each other. Student A, who read just an ordinary story, maybe that was a little boy named Fred who read a story about Dick and Jane, his score, how long it took him to read this book, has nothing to do with student G. It's a completely different story. Maybe that was someone named Grace who read a different story. So there's 2 different groups of stories. This is important for you to get that an independent t-test, you're not doing the same person is not reading a story with the name and without the name. That would be a dependent or a paired t-test. So go ahead and take down this information. Now, the first thing you want to do with this information is define the populations, the 2 populations of interest. Now, population 1 is the one that you're really interested in. Typically, it's your experimental group, okay? Whichever one you're interested in, seeing if it has some effect. So that's going to be the population where they read the story with their own name, the own name story. So if I was reading a book, it would have my name, Naomi, in it, and I would read the character with my name. Population 2 is the other population, the population that reads the ordinary story, so the Dick and Jane story. So those are your two populations. Now, will you ever know the scores from an entire population you're interested in? All kids around the world, if they read these books, because you're interested in the implications of these findings, not just the small sample, that little tiny sample that you're looking at. So you'll never know the information about the population, but you're going to use samples from each of these populations and compare their scores on a continuous variable. Here, our continuous variable is the reading time, the time it takes them to read the story. So your first variable here is which group they end up in, the group with their own name book or the group with the ordinary story. And then your second variable is the continuous variable. And you're asking, is this continuous variable different between population 1 and population 2? You're going to take a sample and look at the means between sample 1 and sample 2 and say, are the means different enough on this continuous variable, the reading time, to conclude that the populations are probably different too? Or is it a small amount of difference and you just attribute it to sampling error and decide, no, stick with the null hypothesis? So you define the populations, then you need to state the hypotheses. The null hypothesis, abbreviated here in scientific notation, H naught, is that mean mu1, so remember mu is the population mean, equals mu2. So when you're hypothesizing, you're always hypothesizing about the population, even though the data you collect is from the sample. You're going to get a sample mean minus sample 2 and two sample means, but your hypothesis is about the population. You're going to use this information and the information you know about standard error, so how far these are in terms of standard error, to answer this question. And then the alternative hypothesis or research hypothesis is that mu1, or the mean of reading score or reading times for population 1, is not equal to the reading times or the mean of reading times for population 2. So you can write this in scientific notation like this, or you could write it out. The null hypothesis is that the average scores in the population for the groups who, or the individuals who read the books with their own name, is the same as the average reading times in the population of the students who get an ordinary story. Now, you remember back when we calculated t, calculating t is the same thing. You're going to take the difference between these means, x bar or m, they both mean the same thing, they're sample means, and you're going to say, is this big enough in terms of standard error? But now you don't just have one standard error. Remember, standard error was the standard deviation of the distribution of all means. Here, standard error is going to be this distribution of all possible sample mean differences, because now you have two groups and you're talking about the differences of those groups, and you're saying, how far is the difference away from 0? Is this difference of these two means far enough away from 0 that you can conclude the population differences between population 1 and 2 are not 0? So that's the test that you're doing with this, the hypothetical test. All right, so let's go ahead and move on. And the top part of t is going to be pretty easy to calculate. You just take the two sample means and subtract one from the other to get the top part of t, the numerator in your t statistic. But the denominator, standard error, takes quite a few steps. So after you've figured out what your null and alternative hypotheses are, what your two populations that you're comparing are, then you're going to want to calculate your comparison distribution. And in the comparison distribution, remember, we're using the t-table, so there'll be a zero in the middle, and then the standard deviation of the differences of those means, right? Or the standard error of those differences. You can see it's down at the very bottom of standard deviation of the distribution of differences of the mean. Standard error of the differences of means is the bottom step on this PowerPoint, but you are going to go through several steps to get there. So you remember, first you have to have the variance of each population. You don't have it here, so you estimate it first with your sample information. Remember, when you're estimating the variance, you've already learned how to do this, but you divide by n-1. Don't forget that. After you have the estimated population variance, so the sample variance for each of these groups, then you have to pool the variance. You have to put them together. Okay? After you pool the variance, so that's a combination of the variance estimate of the two populations, then you have to pool the distribution of means. Okay, so this is, remember when we divided by n, or if you take the standard error, you take the square root of the variance divided by n, because remember that variance of the means changes based on sample size. And then once you have that, the variance of the distribution of means, and you've pooled that, then you just take the square root of that. You get the standard deviation of the differences of the means, or standard error. So let's go through the steps of calculating this. It takes a little bit. First, in order to calculate the estimate of the population variance, you have to remember the variance is how far an average squared each score is from the mean. So you have to calculate the mean first. So let's go to the drawing board. And here's our example. So the first step, you need to calculate the mean of reading time for this group, the mean of reading time for the second group. So go ahead and pause. You know how to do the mean, calculate it. Okay. And then come back and check your answer. So the mean of the first group is 6. The mean of the second group equals 9.6. So there you have the two means for each group. You can also just write this as x1 or m1 equals 6, x2 or m2, remember these are the same thing, equals 9.6. Now you just add them up and divide by the number. Now, a couple other things to note. N. So how many do we have in this first group? N, we have 1, 2, 3, 4, 5, 6. So here, n, the sample size equals 6. Here we only have 1, 2, 3, 4, 5, n equals 5. So what are the degrees of freedom for this first group? Remember, the degrees of freedom are the values that are free to vary. If you know the mean of the group, you have it's n minus 1. Remember, we learned degrees of freedom before, so your degrees of freedom for this group equals 5. Degrees of freedom for this group equals 4. So those are important things to calculate first. Now, in order to get the variance, you know how to do it. You take the mean, you take each score minus the mean, square it. You sum the squares, divide by n. So go ahead and pause, calculate variance for each of these. You're going to calculate variance here and variance here. Remember, divide by n minus 1 instead of n, since we're estimating the variance of the population. So go ahead and pause it, calculate variance, and then come back and check your answer. All right, and the answer here should be the variance is 5.6 for this group, and the variance for this group equals 19.3. So that's, if you didn't get that, maybe go back, review a little bit. You should all of this should be pretty basic, from the past. You should know how to do this easily and be able to move on from this point. So once you have this information, then you can pool the variance. Right? And I'm going to go back to the PowerPoint and give you a formula for pooling the variance. This is kind of like weighting the variance, because I could just average the two variances, but you know that there's a different n, or a different sample size in each of these groups. So it would mean that one of these groups would affect the variance more than the other group. So instead we're going to take the proportion of n, so you're going to take the degrees of freedom for that group divided by the total degrees of freedom. So it's the fraction of the entire group that group represents as far as sample size, and multiply it by its variance. Add it to the fraction that the second group represents as far as sample size, times its variance. Add them together, and that becomes your pooled variance. So it's your pooled variance estimate of the population. So let's go ahead and try this. Your degrees of freedom total. Now there's degrees of freedom total on the bottom. Anyone know what that is? You're right, it's just the degrees of freedom for the first group plus the degrees of freedom for the second group. So our degrees of freedom for the first group was 5, degrees of freedom for second group was 4, so the total degrees of freedom equals 9. So go ahead and try and calculate this pooled variance. Just plug in the first variance and the second variance, plug in your degrees of freedom, and you should come up with a pooled variance. Go ahead and pause the video, come back and check your answers in a minute. All right, so let's see. You should have taken this first variance, plugged in 5.6, and then plug in the degrees of freedom of 5, divided by the total degrees of freedom. That was 9. So 5 divided by 9, multiply it by 5.6. Second degrees of freedom was 4 for the second group. Total degrees of freedom 9. So 4 divided by 9, multiplied by 19.3. So you end up multiplying this, you get, if you multiply this whole number, you end up with 311 here and with 8.58 on this side. If you didn't get that so far, you need to go back and recalculate this. Then you add 311 plus 8.58 and you should end up with 11.69. So you add these two numbers together, get 11.69. That is your pooled variance. Okay, your pooled variance. Now this is just of the scores of the population. So we haven't even got into the means yet. Remember when we calculated standard error, you divide by the n to get your spread, and then to take it back to the standard deviation of those means, you have to take the square root of it. So we have a couple more steps to go. This is just to get your pooled variance of the scores. The scores, we're not even to the means yet. Okay, so let's go back to the PowerPoint. The next step is to take the pooled variance, and you're going to eventually get to the distribution of the mean differences of those scores. So you, just like before, when you take the variance and divide by n to get the spread of those means, we're doing the same here for each group. But instead of dividing by the total n, for each group you divide by the n of that group. Okay, so let's go ahead and go back to the drawing board in order to calculate. So you have your pooled variance here. Let's just plug it in. Back on the drawing board, let's plug it in here. Your pooled variance, you have 11.69, and you just put the same pooled variance in each of these spots, divide by n of 1. You remember, you go back to your n, go back to this group here. We have the n of 1 is 6, n of 2 is 5. So you divide this one by 6, you divide this one by 5, and those, you're going to end up with your distribution, or your variance of the means for the first group, your variance of the means for the second group. Once you have that, you should have gotten, for the first group, you should have gotten 1.95. For the second group, this variance of the means should have been 2.34 if you divide this by this and this by this. Now, to get the variance of the differences of the groups, because we're looking at the differences of those means, you have to combine the two of these. So you're going to combine this one plus this one. So you combine each of these, the variance of the means for the first one, 1.95, plus the variance of the means for the second group, 2.34. You add those together, and you should end up with 4.29. Let's see. So go ahead and double check your answer here. What we were doing was taking the pooled variance for one group, which is 1.95, plus the pooled variance for the second group, 2.34. Add them together, and we have 4.29. So that's the variance of the differences of the means. Now remember, we have to take it back to our original units. So we have to take the square root of that to get the variance of the differences. This is what we use for our spread of the t-scores. So you take the square root of this, square root of 4.29, go ahead and do it, equals 2.07. That is the standard error. That's the term that will go in the bottom of your t-test. This is the big happy term, 2.07. There were a lot of little steps to get there. So you might want to stop, review, make sure you have good notes on these steps, because there's a lot of little steps to get the spread of the standard deviation of the differences of the means. So it's like standard error, but it's for the different pooled standard error of the means for each group. Okay. So that 2.07 is going to go on the bottom of your t-statistic, your t-test. You'll have the differences between the means on the top, and then this pooled standard deviation of the differences on the bottom, 2.07. All right. So now your next step after you've calculated this, is to calculate your t-score and to look at your comparison, your cutoff. So the cutoff on your t-distribution, remember, in the middle, let's go back to the drawing board, the middle of your t-distribution, we have 0. And then we're going to it changes based on the degrees of freedom. So here you use the degrees of freedom total, which is the degrees of freedom for the first group plus degrees of freedom for the second group. Degrees of freedom equals 9. So what you will need to do is look for your cutoff scores on the T table in the appendix of your book. Let's go ahead and look, open up your book to the appendix. And here we have the handy T table. And we're doing a two-tailed test. Remember, my hypothesis was not equals or equals. The null was not equals, and we were looking at both directions. Does reading the book with your name, improve your scores, make your scores worse? Is it different than reading a book without your name in it? So here's our handy T table. Go ahead and get yours out. You may not be able to see this on here, but you should be able to see it in your book. Go to degrees of freedom 9, and you're going to want to scroll over to. Don't go with one-tailed test. We're using two-tailed tests. So scroll over to the two-tailed test for degrees of freedom. Let's set alpha at 0.05. That's pretty much standard. Let's use alpha of 0.05. So the cutoff is 2.262. So you see that T value right here says 2.262. So you need to mark that on your drawing, 2.262. Let's mark that on your drawing here. T, and I would just mark it T cutoff so you don't forget what it is. It's not your T calculated T, it's your T cutoff. Now this is positive 2.262. Now remember, since we're doing a two-tailed test, you will also need to put one on this side, and it's negative 2.262 T cutoff. Now you're only going to reject the null hypothesis if your calculated T test falls outside, so this direction, outside, let's move this up for you, of this cutoff area. So you've calculated your T cutoff. Now the next step, if you go back to the PowerPoint, the next step is to calculate your actual T score. This is your test statistic. This is the difference between your two sample means divided by that pooled difference of all possible means. So you've already calculated that bottom part of your test statistic. That number, let's see, where did it go? Oh, it's on here. So that's the 2.07. So now back to the drawing board. All you have to do to calculate your T is take mean 1, which was, going back to our information here, back to our information here that you calculated at the beginning. You have mean 1, which is 6, minus mean 2, 9.6, and divided by this 2.07, and this is T. Remember the T, you just calculate mean 1 minus mean 2. Now let's see. We actually called group 1 our own name story, so you want to switch these. It doesn't matter because either direction you're doing a two-tailed test, but if you're going to call group 1 your experimental group, reading your own name story, we'll go ahead and switch these around. So we'll do 9.6 minus 6. And let me just clean this up a tiny bit for you. So T equals mean 1 minus mean 2 over the standard deviation of the differences of means. So your mean 1 was 9.6, your mean 2 was 6, divided by 2.07. So go ahead and calculate this. We have 9.6 minus 6 equals 3.6 over 2.07. And you end up with a T value of 1.74 or 739. I just rounded 1.74. I'll write 739 on here just so you have the whole thing. 1.739. So T value is 1.739. Now you've calculated your T value. Now you need to take this T value back to your drawing of the distribution with the cutoff and plot it on there. So here you have your cutoffs for the T distribution, and you have a T value of 1.739. So that means, if you remember your standard deviations, here's 1, here's 2, the cutoff's at 2.62. So you plot your T value, I'm going to go ahead and put it in red here, at 1.739. So it's not quite to the 2 here. So this is your t value, or your test statistic, equals 1.739. And so you look at, did this test value, did your t value pass the t cutoff? No, it didn't pass the t cutoff, so what do you do with the null hypothesis? Do you decide to reject or retain? So remember, you only reject the null if you get off in this area that's not likely by chance if the populations have a difference of 0. Okay, so remember, the further you get from 0, the more of a chance that your populations don't have a difference that equals 0. The further you get into those tails, the more likely it is that the populations are different. It's possible to get that far into the tails drawing from 2 similar populations, but it's not likely. So you use this probability based on the standard deviation of those mean differences. It did not pass that critical cutoff. You retain the null, and you conclude there are no differences between kids reading books who have their own name in them and kids reading books that have just Jane or Dick or the normal books that they read. Okay. All right. So you might want to go through the homework, practice a couple times, take some notes on the steps of calculating a t-test, but basically that's what you do. Now you already know the difference between 1 and 2 tail tests, so there are variants of the independent t-test. If you were doing a 1-tailed test, testing a hypothesis that predicted above, you would only use the 1-tailed cutoffs from your t table in your book, and you would only reject if you pass on the right side. The left-tailed test is the opposite. The 2-tailed test is the one that we went through today. So a couple of things I want to talk about are assumptions of the t-test. Now, assumptions are things that the test is based on. In order to use this test, it's based on a couple of things being true about the population. And we hope that we've met these assumptions. Otherwise, if you don't meet these assumptions, if you don't have this information that's true, the test doesn't work. It's not going to give you accurate information. So the assumptions are that the populations, both populations 1 and 2, are both normally distributed. Now, do you ever know this, for sure? No, but we estimate this based on the distribution of the samples. So if the samples are approximately normally distributed, then we can assume the populations are probably normally distributed, and we go, okay, we've met the assumption. And the second assumption for an independent t-test is homogeneity of variance, or that the spread, the variance of the 2 populations, population 1 and 2, are equal. Will we ever know this for sure? No, but we can test this using the sample variances. So we want our sample variances to be close enough that we conclude the differences between them is minute enough that the populations probably have equal variances. Because when we pool the 2 variances, we're assuming they're both the same, and we're kind of averaging the 2 variances, but we're making this distribution based on the average of those 2 variances, assuming that they're the same variances. So there are tests to do this. We're not going to get into how to do these tests in this class, but just know that you should meet these assumptions. You can look at the distribution of your samples and estimate the distribution of your populations, hope that your distributions are approximately normal and the variances are approximately the same in the samples, because that means that they're likely to be the same in the population. The homogeneity of variance is often abbreviated, the assumption of HOV. So I always think when I'm driving, in the carpool lane, it says HOV up there, and I go, oh, I must have met the assumption for my t-test. So you take a look at that next time you're driving through there. In fact, I didn't even know what the HOV on those carpool lanes stood for. I had to look it up because all I thought of was homogeneity of variance. I found out it's high occupancy vehicles. So there you go. All right, one more thing, effect size. You're familiar with this effect size, the difference between the means divided by the standard deviation. But here we don't have population means and standard deviation. So this is not the effect size you can use for this sampling with the independent t-test. You have to substitute some numbers, some estimates for this effect size that you're already familiar with. So let's go to the next slide, and you can see here's what you will use when you're estimating the effect size for an independent sample t. You'll use the differences between your 2 means divided by, instead of the population standard deviation, you're going to divide by the standard deviation pooled from your two samples. So remember how we calculated the pooled variance? All you have to do is take the square root of that pooled variance, and that gives you the pooled standard deviation. So this is how you calculate the effect size for an independent sample t. And just once again, what the effect size is measuring, it's measuring how big of a difference are these two groups from each other. Okay? Is it a tiny difference? Even if it's significant, remember you can have a powerful enough study to find a tiny difference, reject the null, or is it a medium difference, or is it a huge difference between the two populations? So that's what you're estimating with effect size. Not only are the groups different from 0, which that was your null hypothesis, are the two groups differences you're not 0, but is it a tiny difference, is it a medium difference, or a large difference? Now, there are some issues with the t-test. It's not perfect. There's a problem because we put the cutoff, so if you're doing a cutoff of 0.05, which is pretty much agreed on, or 0.01, which is a little bit more conservative, and you look up that number in your t-table, this is assuming that you're only doing one t-test. Because we know that if you were to take a sample over and over and over and over and over, that level, what you know about type 1 error is that 0.05 means 5% of the time you would end up getting a difference in that tail. So having that extreme of a difference between your sample means, even if the populations were identical. And so there's a problem there, because if you only take a sample once, you know that there's a 5% chance that you're making a type 1 error. That's fine. We accept that we're not always 100% sure, but we're at least 95% sure there. But if you are doing multiple t-tests with the same data, so say that you have 20 different issues you want to look at, and you make all of these different t-test comparisons, by running more and more and more tests, this table that you use in the back of your book is assuming you're only doing one test and cutting off the error rate for one test. So you're multiplying that amount of type 1 error, and eventually, by chance, you're likely to end up in that tail and reject the null when you shouldn't and make a type 1 error. So keeping this in mind, people want to limit the number of t-tests that you run. You shouldn't just run multiple t-tests on everything. And in fact, there are corrections. If you are going to run multiple t-tests, there are many corrections. We're not going to get into those in this class. If you take an advanced statistics class, you'll get to learn those corrections. But essentially what they do is they decrease alpha, or their significance level, to make up for each additional test that's being run, because we realize that you're going to end up inflating that type 1 error, or the tails, this is my normal curve, the tails of that normal curve, and so they decrease that, adjusting for the inflated type 1 error. The t-test also isn't great, as I told you, if you have more than two groups. If you were comparing 3 groups, maybe kids who read a combination of books with their own names and their friends' names in it, or books with just their own names, or books with names of kids they don't even know. So then you have 3 groups. T-test doesn't work for that. But you're lucky, we have ANOVA, analysis of variance, and that's what we'll be covering next week. So hopefully you've gotten everything you need to get for t-tests, and we'll be moving on to ANOVA next time I see you. All right, it's been great. Can't wait to see you again.